Hello, everyone. Here I am again, and now I'm going to lead you a little bit to the Maastricht assessment, because I thought that maybe not all of you know that there are some fundamental differences between Mars and Earth. And this is very important to know, because it's by knowing Earth that scientists of NASA collected the data that arrived from satellites or from the rover that first explored Mars, collected the data and then interpreted them. And to interpret the data of an unknown, and Mars is still relatively unknown, of an unknown planet, you need to somehow have in mind something that you know. So you can compare the data from Mars to something you know, which is Earth. So what are the differences and the similarities between the two planets? There is one very important thing that those of you who are not geologists perhaps do not know or don't remember. Earth, as something called plate tectonics, is a planet that is alive. It moves. Mars doesn't. So I call it dead. I mean, it's not dead, but it's like you have something alive and keeps moving like this and that, and something that is totally quiet like this. That's Mars. So what's plate tectonic? You know that Earth has a center, and then it's got a mantle. Well, my Earth looks more like an egg, but. And on the mantle, above the mantle, there's something called the crust, and we live on the crust. So the crust is quite rigid, right? And the mantle has a part that's more plastic. And here it's very hot. And let's imagine, like, a very hot core. Somehow this causes motion in the mantle. And this motion have an impact on the crust. The crust breaks because the crust is rigid. So what might happen with that? Something that is very important, because now I'm going to show you the sea, the land, and this is the bottom of the sea, and is a plate that is colliding with another plate, a continental plate. So they cannot just bang. This goes under, and this folds a little bit like this. It moves by moving under, so the ocean plate moving under the continental plate. It brings down sediments, little particle of rocks, and organic matter and organisms that deposited in the sea down, where the temperature rises, because here is hot. Temperature rises, and in the end, this material melts. It melts and it rises up. And when it rises up, it forms volcanoes. and volcanoes erupt. Now, there is also something else which goes down, it's water. And when it's heated, also it rises up. And so you get the interaction between hot water and rock, and these form hydrothermal deposits of minerals. Hydrothermalism is very important. You have hot water, so volcanoes and hot waters, geysers maybe. They are important because where there is this hot water, many times you find a specific type of organisms that love very much to dwell in the heat. So this is something that on Mars doesn't exist, or we don't know of it. Plate tectonics. Plate tectonics means that we have volcanoes, we have hydrothermal water, everything is in movement, and it generates also carbon dioxide. Volcanoes generate CO2, which goes in the atmosphere, and so helps to keep the Earth warm. On Mars, this doesn't happen. Now, with plate tectonics, we don't just do that, have volcanoes, but if it goes on, and we have two colliding plates, here it can build mountains. On Earth, there are many, many mountains. There are also lots of mountains on Mars. But if you think about it, and you will see in the maps of Mars that you have to look at, to study for your assessment, but also just simply Google Mars, and you see that the planet is like this, and it's got all these round features. So these round features are craters. At the bottom, and then it rises up. And if you make a section, think of seeing it, this is seen from above, just think of slicing it up, and it would look like this, like a ball. That's a crater. What's a crater? The crater is the product of the impact of a space body, like a meteorite, on the planet. Now, there aren't many craters on Earth. On Earth, you see lots of other features. You see calderas. What are calderas? And what's the difference between a crater and a caldera? A caldera is, you have a volcano, and on top of the volcano there is a caldera, meaning, like here the magma comes out, and sometimes what happens is it can blast all the volcano, and you're left with a lake. All this is gone during an eruption, and the caldera is being filled maybe by a lake. So look, for example, you can Google Earth and look at Taupo, New Zealand. That is a caldera filled by a lake. So these are the big differences. Lake, caldera, or you have a volcano with, there is a sort of a depression at the top, but it's due to the eruption of the volcano. On Mars, you have craters. And why is it that you preserve craters, or these craters, for billions of years? At first, I didn't think about it. I just give it for granted. But that is also the difference between Mars and Earth. On Earth, a mountain that formed 2 billion years ago, now it's flat. Think about Australia, it's very flat. It's a very old continent. All the big mountains that once we had are gone. Because there are two things acting on Earth which have to do with water. What is erosion? Well, erosion is a process through which you basically dismantle mountains, and you make mountains, you transform mountains in sand or pebbles or even smaller grains like silt. But erosion implies that you break up a rock, but also then you transport the products. Now, the transport of the products of the erosion, and let's suppose that the products are from a rock you get into sand. Transport is not just, or not only water. So water does a very good job. Rivers do a very good job in picking up sand and transporting all the way to the sea. And then waves do the same. They put the sand back onto your beach and then back again. But wind also does that. And this is important because on Mars there's no water, but on Mars winds are very strong. So what does wind do? Wind picks up small particles, less than 2 millimeters in diameter, and they pick them up and then, carry the particle through the air, and then finds an obstacle and starts depositing this, because the velocity decelerates if you find an obstacle. So it cannot carry anymore the particles, drops them and starts to build dunes. A dune will move because the wind will pick up the particles from here and deposit the particle here, pick up from here and deposit there. And by doing this, it will always erode this side and deposit this other side. So the dunes will move, keep moving. If you look into some of the craters of Mars, you will find lots of sand dunes, lots of dunes. There are large, huge dune systems on Mars, which means that erosion exists, but it's not the means of transport, or even the means of erosion itself is not water, it's wind. Let's get to Earth. On Earth we have, again, erosion, but this time we use water. And water is doing much better, there is more erosion on Earth due to water than to wind, but there is also another very important process of landscape shaping. This one. It's called weathering. Weathering differs from erosion because the products of the rock breaking remain on site. They are not transported. So on Earth, this is how you create soil. You weather a rock, and the product is soil. Oh, this doesn't happen today on Mars because there's no water. So weathering, or hydrochemical weathering, meaning that the weathering is carried out by the interaction between water and a rock, on Mars doesn't happen. But let me get to the important part of this. As I mentioned to you at the beginning, we need to know what's happening on Earth to interpret the data we have from Mars. And what are we looking for? We look for this on Mars: water. And because there is no visible flowing water, there's no evidence to that, we look for fossil traces of water. And where do we look for them? In minerals. So I have to put water into a mineral that has no water to create another mineral, which, having this in its formula, will tell me, scientists from NASA, for example, that if I find a hydrated mineral on Mars, there must have been water when the mineral formed. So when Mars was more active and had the volcanoes, there were minerals coming out with the magma, which you find also on Earth. And those minerals are called pyroxenes. A formula for pyroxene, I have to look at it because I don't remember by heart, but a formula is this. You have magnesium, you have iron, and then you have silica, silicon, and oxygen. So if you can see this, the formula of this mineral, there's no water in it. Magnesium and iron, which you find off Mars, silicon, and oxygen. Now, this is a very common mineral also on Earth. You find it in basalt. Now, what happens if water interacts with this mineral, which is what happens on Earth? You transform. So this is a very compact mineral, sort of green-looking, hard. Now, if you put water in it, you have to, like water is a big molecule, so you have to stretch and change the structure of the mineral. So from a pyroxene, the mineral will be turned into clay. So we still have magnesium. We still have iron. But now, clays are a lot more complex than a pyroxene, so I will have to balance the formula, but then we still have silicon. We also have aluminum on Earth. And then here is where we start doing the trick. We have to put the water in it. Okay? Hydrate the mineral. So the whole thing is it picks up also some oxygen. It picks, and here it is. And this is part of the water molecule, OH, and then H2O. We have formed a clay. And now to balance the equation, I think, yeah, this is 2, this is, I think, is 4. Yeah, it's 4. I still remember it. And the oxygen is 10. And this should be okay. Yeah, it's okay. So magnesium and iron, silicon, oxygen. But what we put is these two, this OH and H2O, derived from water. Now, when the scientists from NASA looked at the data coming from the chemical, like the chemical data from the satellite, they found clay. So they have the pyroxene, but they also found the clay. And that is bingo. That used to be water. So it's a very good indication because it's telling you that weathering was happening. And if weathering was happening, chemical weathering, hydration of mineral, it's good speculation, or it's a good speculation to say at a certain point in time there was water. And when was that point in time? Well, again, I told you that we don't, on Mars we don't have any more water, and erosion is only by wind. So erosion is, and weathering, weathering is not occurring, but erosion is probably a lot slower than on Earth. That's why you can have huge mountains and you preserve craters. And some of those craters somehow have been dated, and they are 3 billion years old. So you potentially preserve a feature of the landscape of Mars for billions of years, which you cannot do on Earth. And that's another fact you can add to our way we are actually using scientific thinking. So you put together the fact that there is evidence that there was water on Mars a long time ago. There is evidence that weathering occurred, erosion still occurs, but it's not as efficient as on Earth. And now we have evidence also of the preservation of giant impact craters on Mars. And whereas you look on Earth, you almost don't see them. You really have to know that they are craters. So all of that is preserved because this water is not doing what it does on Earth. I also told you that there are minerals that were hydrated. Mars today is quiescent or dead, as poor Mars labeled it. But in your hunt for evidence of life on Mars, one of the things I want you to hunt for is to check if you have volcanoes on Mars. And then we don't know if there was plate tectonics or why we have those volcanoes, but the whole idea I want you to get is volcanoes are important. We look for volcanoes on exoplanets, the planets that are outside the Earth. We look for that activity. So we are looking for several hints. It's like a mystery. And we are hunting for evidence of weathering, and particularly of weathering by water of minerals on Mars. But then we are looking also for something else, which has to do with transport. So it has to do again with this erosion. The morphology of the landscape on Earth is shaped by water. And you know it. You go and you see the waves shaping your coasts, and you see the rivers. You go into the Hunter Valley, and there is the Hunter River. And the Hunter River, what does it do? It erodes on the mountains, and then it transports and forms this flat valley when it dumps the sediment that it's transporting. So Earth has plate tectonics. So I told you, oh, I want to use the orange one again. It builds mountains. So as soon as you have mountains, you have clouds, and you have rain or snow, and this collects into rivulets and goes down, and then it starts organizing itself in rivers. So if I look, again, this is I look at a mountain, but let's think we are looking at it from up above. So this would be the river, small little rivulets coming down from the mountain, and they all converge in a major valley. So they start forming what's called a drainage. So the crest of the mountain will be here. And then there might be another valley, another mountain like this. So rivers would also come down off the flank of this mountain and converge in this river and make it a little bit bigger. And maybe there is another ridge here. And here are river coming down, they converge with this and become even larger. And by the time it gets into a more gentle slope, so the mountain, now we are far away from the high slope of the mountain, we have a gentle slope. The velocity of the water will be slower than here because the slope is more gentle. So it will get rid, deposit the larger particles that cannot transport. At a certain point in time, the river actually, or in space, the river might start to do something like this, meander. It's becoming sinuous. And then it might encounter a lake, like a caldera lake. And because it still carries material, and this is a body of still water, what it will do is it will deposit, and it will form a shape like this called a delta. So we know that a delta can be formed when a river enters in a lake or in a still body of water like a lake or in the sea, and the river is carrying a lot of material, so the river will build into the lake or the sea. It's called progradation. And a delta has this can have this lobate shape. So if we see something like this lobate shape in a large concave feature, a basin, we might think that there was a river that entered into a lake and deposited the sediment that used to transport. And that is a morphological indication that water may have existed. Now, as many things on Earth, there can be different explanations, because the same or a similar feature may be created potentially if a flow of ash with lots of gas in it flows down a volcano and enters into a lake. How do we distinguish if one is a delta transported by a river and the flow is water, or if it is a delta that has been built by a flow of ash, a very fast flow of ash with, as I said, lots of gas in it? We look at the minerals, and if it is a delta, we might probably find the minerals containing water. And if it's just lava with no water in it, maybe we just find the silica, magnesium, aluminum, potassium. So that is the importance for you to think like the NASA scientist. So you see features on Mars that resemble features on Earth. And you start clicking, something clicks in your head. Say, oh, I have already seen that. It looks like this, or it looks like that. It looks like sand dunes, it looks like a delta, it looks like a meandering river, there is a drainage pattern. But then you want to be sure. And to do that, you need the chemistry. Because the chemistry is that piece of information that gives you a best certainty that maybe indeed there was water. So that feature was created in the presence of water. It's the product of erosion and weathering, or not. And it's exactly the reason why you are going through this assessment that as much information, but at the same time is leading you through a process of scientific thinking, and is telling you that you cannot just hypothesize when you see a feature. You have to formulate an hypothesis from data that is being presented to you. And you test your hypothesis by comparing what you find, or the information you are provided to related to Mars, you are comparing it to something you know about Earth, because that's the only Earth is really the only planet we know very well, and actually not so well, because there are so many things that we still do not know. But on the base of that, on the base of comparison, then you test your hypothesis, and in the end you can say, like the NASA scientist, yeah, that's exactly where we want the rover to land, because it's where the rover might find evidence of past life.